Hello, and thank you. Welcome to the last session on the last day, parallel session number 10, Future and Continued Exploration of the Moon and its Surrounding Area. And thanks for staying. The session chairs will be myself, Pamela Clark from JPL, and Richard Miller, who's sitting in the front row from the University of Alabama in Huntsville. And the first speaker will be Raul Monsalve to talk about the EDGES and DARE precision cosmology experiments.
Thank you very much for the opportunity of presenting this talk, and thank you for attending. So I will talk about cosmology, and this is the first session about this topic, and this is the first talk about this topic. So I will start with a very general introduction. Hopefully you know about the cosmic microwave background. So that's the first light emitted in the universe, roughly 13.7, 13.8 billion years ago. So in this figure, I'm showing the CMB at the top and time moving down until the modern universe at the bottom, okay? And in cosmology, what we want to do is to understand large-scale physics and from the early universe. And in this case, what we are interested in is roughly between 100 million years after the Big Bang and 1 billion years after the Big Bang. And during that period, the neutral hydrogen in the universe that was created very early on transformed into compact objects such as galaxies and stars and black holes and all that. So what we want to do is to understand that process, how the universe went from diffuse gas to compact objects. And to do that, we need to look at the gas, the properties of that hydrogen gas. And one of the key elements that we can take advantage of is the 21 centimeter line. So that's a spectral line at 1.4 gigahertz. Okay, so between the CMB and our telescopes, there is some neutral gas, neutral hydrogen emitting this spectral line. So if we want to understand what happened back then, let's look at that line at that frequency. But it happens that there is something called redshift. So as we go back in time, we need to look at that spectral line at lower and lower frequencies, because as the redshift goes up, the frequency goes down according to this relationship. Okay, so if we want to learn about the universe between redshift 6 and 35 roughly, or before the first billion year, we need to look at frequencies between 200 and roughly 40 or 50 megahertz. Megahertz, that's the VHF range. So, and if we look at that frequency range, we should be able to see the hydrogen line, how it evolved in time. So in this figure, I'm showing on top the redshift scale, and here on the right side, we have a redshift of 6, and around here we have a redshift of 30. And that corresponds to frequencies at the bottom between 50 and 200 megahertz. And there is a prediction of how the hydrogen line evolved with time due to those physical processes in the early universe. So the amplitude of that signal is extremely small in the millikelvin range, okay? But we still want to do that measurement to study this physics. Nobody has done this measurement. There is no detection of this signal yet, only models, unfortunately. And so there are, on top of the signal being really small, there are some extra difficulties. One of the difficulties is your instrument itself. Your instrument needs to be extremely well calibrated, understood, and removed from the measurement. We don't want any spectral structure introduced by the instrument itself to be left in your calibrated measurement. So instrumental calibration in itself is difficult. It's one of the main challenges of this type of measurement. On top of that, we have very strong foregrounds. We are looking at this signal coming from the early universe, but we also have signals originating right in front of us, in particular due to galactic synchrotron radiation. This is a foreground for our purposes, and we are talking about temperatures of 1000 kelvins or more. So these are orders of magnitudes above the millikelvin level signal from cosmology. So this is another challenge. Another challenge is the ionosphere. From the Earth, when we receive the signals from space, we need to deal with effects due to the ionosphere, and in particular, emission of signals from the ionosphere, absorption of signals that go through the ionosphere, and also refraction. In other words, we are looking with our antenna at some solid angle in space, but we don't really know how that solid angle looks like from outside the ionosphere. In other words, there is some perturbation that also transforms from space to frequency and introduces some spectral structure that we cannot correct for. And finally, there is radio frequency interference. In the VHF range, we have FM radio, we have TV signals, and we have satellites that contaminate the frequency band that we care about. So on top of the strong foregrounds, we have our own interference to deal with, and we are talking about extremely strong signals that saturate our receivers potentially. So even with all that, we still have, and when I say we, I mean the scientific community has produced a few efforts to observe the signal from the ground. One of them is called EDGES, the experiment to detect the global EOR signature. And so this is located in Western Australia, and because over there, it's a relatively radio quiet location. That means that signals from artificial transmitters, radio, TV, and all that, are as low as they can be on Earth, okay? And so EDGES consists of two experiments, EDGES low band and EDGES high band. And between these two experiments, they cover the frequency band between 50 and 200 megahertz, attempting to detect this millikelvin signal from cosmological times. Here I have a picture of the low band antenna. Now, these are single antenna experiments because we want to observe the spatially average contribution, okay? And in order to do that, we need an instrument that has a wide beam. And to achieve that wide beam, we only require one antenna. At the same time, this antenna needs to be wideband, okay? So it is wide field, but also wideband in frequency. So this is the low band antenna. And for reference, these are two panels, and the total length of the two panels is 2 meters. Now, and below the antenna, we have the first stage amplification, and here, inside this box, underneath the ground plane, which is this white metal structure here. And this is the high band antenna that covers between 100 and 200 megahertz. The length of the two panels combined is approximately 1 meter. So in terms of status, with EDGES, in which I participate, we are reaching sensitivities below 100 millikelvin already, after modeling and removing effects from foregrounds, ionosphere, and the instrument itself, basically the challenges that I told you about before. And these sensitivities are of the same order of magnitude as the predicted cosmological signal. So we are achieving very interesting results already. So modeling and removal of these effects is imperfect, unfortunately, and we continuously work on improve the sensitivity by understanding these effects better and better. To do even better than that measurement from the Earth, we need to go to space. So let me introduce you the DARE experiment. DARE stands for Dark Ages Radio Explorer, and it's a next generation experiment led from the University of Colorado Boulder. And in summary, it is a precision cosmology experiment to be proposed to NASA in December 2016. It's led by Professor Jack Burns from Colorado Boulder, and the plan is to observe for roughly 1,000 hours from orbit above the lunar far side. And why do we want to do that? As I told you, the ionosphere presents or represents a challenging aspect to deal with in these measurements. So going to space in itself allows us to avoid ionospheric effects. But on top of that, the moon itself protects us from artificial radio frequency interference that comes from the Earth, that we ourselves produce. So we would use the moon to shield our instrument from that artificial radiation. So observing from the lunar far side solves the ionosphere problem as well as the radio frequency interference problem. And on top of that, we will be applying lessons from the ground-based EDGES experiment. So people that have worked on EDGES, myself included, will transition to DARE to get to the next level of sensitivity to do this precision cosmology measurement. And the observing band for DARE will be roughly between 40 and 120 megahertz. So it will cover the band where we expect most of the spectral structure to be. This absorption feature and this emission feature due to the interesting physics in the early universe that we really want to study. And one important aspect of this experiment is that we are preparing a data analysis pipeline that includes most of the statistical effects due to noise in the measurement, systematic effects from the antenna properties, the receiver properties, and all that, and all the way to the physical parameters that we want to estimate and understand. So in this triangle plot, I'm showing you, this is produced from simulated data, where we are trying to estimate parameters from the physics of the early universe, according to very sophisticated predictions. So here we show that with 1,000 hours of observations, we can, in principle, estimate with precision and low biases these physical parameters. We are working on this pipeline to improve it and to make it as realistic as possible to incorporate all the instrumental effects, etc. So I will leave you with this. There we'll answer, among others, when did the first stars ignite? When did the first accreting black holes turn on? And when did reionization begin? Thank you very much.
This paper's open for questions. Yes.
How much can your sensitivity for the edges detector improve? And do you, I think I know the answer to this, and do you run the risk of doing it so well that you cut into what you could possibly do for DARE? I think the answer is no, but I'm curious how much better you can get.
Right. We continuously take data with edges and we continuously improve the instrumentation. We want to do the best we can. And so at the moment we have numbers, sensitivity numbers that are even lower than this. In other words, we are approaching the detection level. So we really believe that we can at some point reach the detection level and hopefully do a detection. But a detection is different from doing precision cosmology. We want to do precision cosmology, we want millikelvin level, so therefore we want no RFI, no ionosphere.
Yeah, and that was Richard Miller, by the way. And please identify yourself if you remember to do so. So are you, do you have any idea what how much improvement you can expect in sensitivity? And also, what is your concept of design? The lunar far side is not necessarily an easy place to get to. I'm wondering if you thought at all about some of the challenges of putting an instrument up there.
With aspect, the instrument itself, or?
Yeah, the instrument, the observatory.
Right.
You'll have to get an instrument there somehow.
Exactly. So we are fully aware of the difficulties of making an instrument that is wideband and that is well calibrated and all that. So with edges, we have roughly 10 years of experience on that. And also there are other experiments similar to edges, not that haven't reached that level, but there are alternatives that we are evaluating. So we need to measure the antenna beam of the instrument extremely well. We are aware of that and we are working on that, and we have realistic designs that will achieve that level. The antenna beam is the main instrumental aspect that we need to take care of, and we are working very hard on that, and so we have estimates that we can do it.
Okay. It gets very cold and very hot on the lunar surface.
Right, exactly.
And it's dusty.
And our team has...
Your big challenge is going to be if you have to make... Yeah. Oh, it's orbiting. Oh. Oh, very good. Okay. Right. Oh, okay. Thanks for pointing that out. Right.
Yeah, but our team has experts on these matters, and we are fully aware of all these challenges.
Right. Okay. Thank you. If that's all the questions there are, I'll introduce the next paper.